Hey there, welcome back. Continuing with chapter 11.1, we're going to actually get into some t-tests. So our goal for today is to be able to create, that's too many words there, to test hypotheses, get rid of that, to test hypotheses about means from one sample data. So to this point, we've learned about confidence intervals for means. We've learned about tests and confidence intervals for proportions. We have not talked about um, significance tests or hypothesis tests dealing with means. So that's what we're going to get into today. So a couple recaps of things that we've already learned. Um, when we're dealing with sampling distributions, because this is, again, dealing with data from sampling distributions, um, the mean of all these many samples, sample means, should be mu. Okay, comes straight on your formula sheet as well. It should be the same as the population mean. Same thing, well, not the same thing, but standard deviation, when we have multiple samples, it's not the same as sigma. It is your sigma divided by the square root of n. So hopefully that comes back to you have to divide it by the square root of n. Which means when we're finding our z-score for data like this, we would be doing our test statistic minus the population parameter divided by the standard deviation, which would be sigma over square root of n. Now, unfortunately, we don't know sigma. We're trying to estimate or like test against a claimed sigma. So we're going to use our sample data when we're finding t. So t is going to, again, continue to go with means. We're going to do x bar minus our mu, which comes from our hypotheses, and use s sub x over the square root of n in our denominator here. Now, keep it in mind, this part right here from our hypotheses. This is what we're going to be working with. We're dealing with means, so we're going to be working with this. But that mu is not the true mu. That's just what we're using from our hypotheses. Okay, we don't know exactly the true mu, but we are trying to test against a certain thing. Now, refresher, what conditions have to be met? Same ones that are always met. We need a random sample of blank. Context. Whatever we're taken from. We do need to know it's an approximately normal distribution, and that can happen, again, a few different ways. We could either say we know something about the population. We could say we know the central limit theorem, our sample size is greater than 30, or we'd have to plot it. Okay? Remember, 3 ways to check. And then if we're sampling without replacement, we have to check the 10% condition. So here's an example. It says, according to research conducted by Dr. Workaholic, high school students work an average of 13.1 hours. That should be per week. Per week. Do AP students at Hamilton High School work fewer hours? That's the question, because they have more schoolwork to do. Use the following number of hours worked from a randomly selected sample of HHS AP students and test at an alpha level of 0.05. Okay? So, how do we go about this? What are all the steps for doing this? Well, if you can turn back to your notes or to your yellow sheet on hypothesis tests, the recipe isn't changing. We still need to state the parameter. We still need to state the hypotheses, name the test, check the conditions, use the formula, get the p-value, and make a conclusion. Okay? But I want to just, before we do this example, draw you to this. This is kind of what we've been working with, dealing with the different tests. So we're going to add one sample t-test for a mean to this. Again, that's our name. Our parameter would be the true, mu equals the true mean blank. And then we're going to get into the hypotheses after that. Remember, we want our mu to be equal to a number. Our alternative hypothesis is going to always be something different, greater than, less than, or not equal to, depending on what the scenario gives you. We want to check those conditions. Random sample, approximately normal, 10% condition. Our formula for t, which I just kind of mentioned before, it's going to still be x bar minus mu over the standard deviation over the square root of x, or square root of n. Make sure you state degrees of freedom when we're using that t-value, because then we're going to have to go get our p-value. Okay? So we have to go either from our calculator, which I find to be easier using TCDF, or you could use your table and get a range. I'm going to make a note there. Actually, no, I have it over here. So key points, 3 ways to confirm normality. We've talked about those. And then use TCDF, or you could use the table B to find your p-value. So let's go back to this situation. We've got this scenario. We've got our data. We're going to start. We're going to walk through the steps of this this recipe for doing a hypothesis test, and we're going to first state the parameter. So we're looking for the true mean number of hours that HHS students work in a week. So mu equals true mean number of hours worked weekly by HHS students. And right away, I'm going to state my hypotheses. Our hypotheses would be that we're assuming it's the same as the national average that was given of 13.1. But our hunch, we're trying to test to see if we have any evidence in this direction, is that the mu for, oh sorry, I'm going to actually add in here by HHS AP students. We're looking at AP students. We think it's less than that because they have more schoolwork to do. Okay, there's our hypotheses. Now, we want to get into checking the conditions. Always checking those conditions. And I have those here. Unfortunately, we do have a random sample of HHS AP students, so that was stated. We don't have anything about the shape, and it's not greater than or equal to 30 for sample size, so we have to draw it out. And I have mine kind of drawn right there. There's no strong skew, or clear all it is. We're going to say okay to proceed. And then 14 is less than 10% of all HHS AP students. We have more than 140 students who take AP classes. So those are met. Now we get into the actual test. This is going to be called a one sample t-test for a mean. And I think I'm going to add that in here. It is there. So one sample t-test for a mean. So we have to find a t-value, and that would be using our average. Now, I didn't give you the average. You actually need to find those. Okay? So using one variable stats, go ahead and find the x bar and the s for this data. Using one variable stats, I got 9.143, and 5.545. So we're going to utilize that in our formula. So I did 9.143 minus the 13.1 that comes from our hypotheses, divided by 5.595 over the square root of 14. I got negative 2.670. If you go onto your table, it gives you a range. Not ideal. So using TCDF is ideal. Because it's a negative, I'm just going to put my lower bound is negative infinity, or negative 1 E99 works. Upper bound is negative 2.67. We're looking for that tail probability, degrees of freedom. Remember, right there is 13. Gives me a p-value of 0.0096, which is fairly low. Now, once you have your p-value, you can make your conclusion. And I'm going to say, based off of that, because 0.0096 is less than 0.05, which is our alpha value, comma, we reject, or I'm going to reject our hypothesis that it is equal to 13.1. We have, or there is, convincing evidence that the true mean hours worked weekly. This is where that context comes in. By HHS AP students is indeed less than 13.1 hours. That doesn't mean that it for sure is, but we have evidence to show that it is from our sample that we have. We have enough evidence based off of all what we looked at. And that's a one sample t-test. Now, it should all be on your yellow sheet, which we just talked about. But we're following the same sort of steps that we've done with tests in the past, just using T instead of Z. Okay, so why don't you take a look at this one, and I want you to try this one on your own. So I'm going to say pause and try. But the problem says, do HHS freshman students sleep more than students nationally? Test the claim at the 90% confidence level when research from Why Are You Tired University, like that, has shown that the typical high school student gets 6.8 hours of sleep on a typical school night, while a random sample of 34 high school freshmen from Hamilton High School averaged 7.6 with a standard deviation of 1.3. Okay? Pause and try. All right. So you have a lot of stuff given in this example, and it helps you hopefully successfully test this claim. So my parameters that the mu is the true mean hours of sleep on school nights by Hamilton High School freshmen. Our null hypothesis is that mu is 6.8, and our alternative is that it is greater than 6.8. The claim is that Hamilton High School freshmen get more sleep than that national average. So let's go ahead and check the conditions. Those were all met. It was stated that we had a random sample. We could use the central limit theorem for normality. That was nice. And it's gonna be close, but 34 is less than 10% of all HHS freshmen. No, so now we go on to actually doing the test. It's a one sample t-test for a mean. We have a t-value. I got 3.588. Using a degrees of freedom of 33, I got a p-value, and I went to TCDF of 0.000533. And that's all that I need to draw a conclusion. Okay? Now, because that number is less than 0.05, or really any reasonable alpha value, we will reject H naught. There is convincing evidence that HHS freshmen sleep more than 6.8 hours on school nights. So that's our test. Now, follow-up question. Do you remember how to interpret that p-value of 0.000533? So let's revisit that. You should have it in your notes or on your yellow sheet, but this is where we're assuming that the null hypothesis is true. Okay, we're testing everything based on that assumption. So assuming the true mean number of hours slept each night. I'm spelling things wrong. By HHS freshmen. Well, I'm going to say high school freshmen in general. That's kind of what we're given, but we're assuming it based off of ours. So high school freshmen. Oh my goodness. Is 6.8 hours, comma, there is a 0.000533, or you could say 0.0533% chance of getting a random sample of HHS freshmen who sleep 7.6 hours or more extreme just by chance from a random group of 34 students. So again, interpreting p-value is all about assuming the null hypothesis is true and then saying we could have only had this happen by chance this percent of the time. Okay? That's interpreting the p-value. Now, next time we are going to talk just a little bit about type 1 and type 2 errors as well. So if you want to refresh that, it's no different than what we've done in the past, just refreshing what those errors are. And that can be done with any sort of tests. This was specifically one sample t-test for means. So that's 11.1a, or sorry, 11.1b. We'll see you next time.